All right, so section 4.1 is on real vector spaces. So what we're going to do in this section is we're going to abstractify the idea of a vector space. So up until now, we've done a very specific example of a vector space in section 3.1, 3.2, 3.3, up until 3.5. So now we're going to take that idea. We're used to working with real vector spaces. Everything in chapter 3 is on real vector spaces. But we're going to now abstractify the definition. So a vector space is actually something more general. If V is a set with two operations, normally with vectors we've got two operations. The one operation is addition, and the other operation is called scalar multiplication. Now addition we define as, this is the one you're used to, adding. It all depends on how you define the sum. The sum you can define in many different ways. In chapter 3 we define the sum basically as summing vectors component-wise. But summing is a more general thing. You can sum vectors in many different ways, but you will use the notation u plus v. That will signify adding vectors, depending on what your law of addition is. Scalar multiplication is very similar. If you take a vector u and you've got the scalar k, you use the notation for scalar multiplication. You use that notation there, k times u. Now, when is a space a vector space? We're going to talk about axioms that need to hold for a given space to be a vector space. So let's take three vectors in our space V, and let's take two scalars. Then we say that V is a vector space, and its elements are called vectors if the following axioms hold. Now there are 10 axioms that you need to check whether a space is a vector space or not. So these are very important axioms. So these are the vector space axioms. The first axiom is closure under addition. Now closure means that if you add two vectors in your space, then the result needs to also be in the space. So that's closure under addition. As an example, if you look at the even integers, now the space of even integers, is it closed under addition or not? Well, if you take two even integers and you add them together, then two even integers added together is again an even integer. So the set of even integers is closed under addition. Then you've got the second property, and that is that commutativity needs to hold under addition. So adding u to v is the same as adding v to u. Number 3 is associativity needs to hold. Now we're familiar with the concept of associativity if you go back to matrix multiplication. Matrix A times B times C, where you take A and B first, is the same as taking B and C first and multiplying that with A. So associativity needs to hold over addition as well. And then you need to have what is known as a zero vector. And the zero vector has the property that if I add it to any vector u, the end result is always u. Okay, so adding it, whether you add it on the left or on the right, doesn't make a difference. It always has to be u. So that's the zero vector. And also every vector in your space needs to have a negative. And what a negative is pretty much is, a negative of a vector is a vector that if you add it to a vector, you get the zero vector. Now again, guys, it all depends on how you define addition and scalar multiplication. And we'll see later that depending on how you define addition and scalar multiplication, it will affect whether your set has in fact a zero vector or not, or whether in fact your set has every element has a negative. Okay, so for vector spaces, every vector has to have a negative. Then you've got closure under scalar multiplication. Now, scalar multiplication here is the set, for scalar multiplication, for the set to be closed under scalar multiplication, it means if you apply the scalar multiplication rule, whatever you end up with at the end needs to be back in the set V. All right, so it needs to be, again, be an element of V. So there we go. Right, so this thing here needs to again be back in V. Okay, so as an example, if you look at this again, if you look at the set of integers and you look at scalar multiplication, is the set of integers closed under scalar multiplication? Well, if you take an integer, if you take an integer 2, right, and you take the real number pi, and you multiply pi with 2, right? Now, a 2 pi, is that an integer or not? That is not an integer. So the set of integers is not closed under scalar multiplication. If you take your scalar to be an irrational number, 2 times an irrational number is going to be irrational, and irrational number cannot be in the set of integers. So that's an example of where the set of integers is not closed under scalar multiplication. All right, next we have the distributivity law with respect to scalars. Adding two vectors and taking the scalar multiple of that sum is the same as the sum of the scalar multiples. Axiom 8, again, is a variation of, not a variation, but it's similar to axiom 7. There you take the sum first over the scalars, and then you take the scalar multiple of the vector u with that sum that you get. And that's the same as, again, summing these respective scalar multiples. Axiom 9, again, is again a associativity product law with respect to scalar multiplication. If you take a scalar multiple if you take the scalar multiple of the vector u, and you take that resulting vector and you take k times that, then it's the same as taking k and multiplying it with m and taking that with a scalar multiple. Taking that as a scalar multiple. Okay, then the last property is this axiom 10. If you take the scalar multiple of u where the scalar is 1, then you get the vector u back again. Now, if you think of traditional vector spaces, the vectors that we've worked with up until now, these axioms seem very obvious to you, and it's obvious because you're used to defining addition and scalar multiplication in a very specific way. However, you can define it in many different ways, and we'll see that depending on how you define it, it will influence how your set or your space behaves. All right, next we have some remarks. A real vector space is a vector space where the scalars are real numbers. Okay, so firstly, a real vector space, it has two operations, addition and scalar multiplication. All the 10 axioms that I just discussed hold, and we impose an extra restriction on the scalars. The scalars need to be real numbers. If you have that, then you're working with a real vector space. Then a complex, similarly, a complex vector space is just a vector space where the scalars are complex numbers. Okay, but for the purpose of chapter 4, we're only interested in real vector spaces. Okay, so depending on what the scalars are, that is going to influence what your vector space is going to be called. All right, let's look at some examples of vector spaces. All right, let's go back there. Some examples of vector spaces. Okay, so the first one is Rn. This is the one we worked with in chapter 3, and this is the one we're all used to. So V is the set of all n tuples of real numbers with usual operations of addition and scalar multiplication. Now, what are these usual operations? Given a vector u and a vector v, how do you add them? You add them like you add normal real numbers. You add component-wise. Okay. And how do you take a scalar multiple? The usual way. You take scalar multiples with respect to the components. So that's our scalar multiple, how it works. We're used to that. Then you've got R infinity. R infinity is just different in R to Rn in the sense that you still have sequences, but you've got infinite sequences of real numbers. Where addition and scalar multiplication is defined as follows. How do you add two vectors? Again, you add them component-wise. Okay, but now we're going up until infinity. And how do you take scalar multiples? You take it per component. So that's how. Those are the ones we've basically used to, and the ones that we've worked with all our lives. Then we've got capital M subscript Mn, which is just all the set of m by n matrices. Okay, and how do you define addition and scalar multiplication? You define it as we've learned in chapter 1. Addition of matrices is, given the matrix U and the matrix V, you add them entry-wise. So adding them, it means you take the entry in the ith row in the jth column of U and you add it to the entry in the ith row in the jth column of V, and you do that for all i's and j's. So that is how it works there. And how do you take scalar multiples? A scalar multiple of U is taking the entry in the ith row in the jth column of U and then multiplying that with a scalar k, and you do it for all i's and j's. So you multiply every entry of the matrix with the scalar k. Right, then you've got f minus infinity, positive infinity. How do we define that? V is the set of all real valued functions, and these functions are defined from negative infinity to positive infinity. And you define addition and scalar multiplication as follows. You do it pointwise. So for a vector f and a vector g, you go and add the two functions f and g pointwise. So you go and f plus g is going to be the function that you take by first determining f in the point x and determining g in the point x and adding them together, and you do that for all x's. And then you take scalar multiplication as pointwise as well. You go and determine what f of x is, and you go and multiply that with a scalar k, and you do that for all x's. So that is how operations in f minus infinity, positive infinity, how it works. Now you can also go and define the finite case, where you take all real valued functions f defined on the interval a and b, where a and b is included, and you also define addition and scalar multiplication pointwise. So you define it very similar to that. And then so that is on the closed interval, but you can also define FAB in the open interval. So it's all functions that are defined on the open interval AB, where A is not included and B is not included. And you again look at the functions pointwise. So f plus g is the function that you obtain by taking f in the point x and adding that to g in the point x, and then doing that for all x's. Right, so those are examples of vector spaces. So what we're going to be looking at next is theorem 1, and we've actually done some proofs of properties in theorem 1. I'll maybe just look at one or two of them. If V is a vector space, and U is a vector in V, and K is a scalar in V, then we've got that the zero scalar multiple of U is the zero vector. k times the scalar multiple of the 0 vector is the 0 vector. The negative of a vector is can be written as that there minus u. And if ku is the 0 vector, then it means that either the scalar k must be 0 or u must be the 0 vector. Now, I'd just like to note that failure of any of these properties, it's a useful way to show that a given set is not a vector space. So you would do that by contradiction. You would assume that suppose I want to show V is not a vector space. You'll take V and you'll assume it is a vector space, and then you will prove, hopefully, that either this property doesn't hold, or that property doesn't hold, or that property doesn't hold, or that property doesn't hold. Okay, so theorem 1 is useful in the sense that you can use it to prove that a given set is not a vector space. All right, so let's, I've done proof of property 1 before. Let's just go and recap. So in a vector space, I'm allowed to only use my axioms. All right, so I mean, you can look at 1 in quite an interesting way. Remember, we said that the 0 vector u, we know that the 0 vector added to the 0 vector is the 0. Well, we know the scalar u added to itself is always u. Okay? Sorry, let me rephrase that. The scalar 0 plus the scalar 0 is the scalar 0. Now, if you go back to your axiom list, now look at this distributive law. Look at that distributive law. So I make the scalar k 0, I make the scalar m 0, and I multiply that with a vector u. What's going to happen? Right? So by our axioms, we have that this distributivity law holds. Okay, so we've got that. And so what we do is 0u is a vector, and in a vector space, every vector has a negative. So let's add that vector to its negative. What we do on the left, we need to do on the right as well. Okay, so we're doing this. So we're adding with the negative of the vector u. Okay, and so from there, what's happening here? What's that equal to? A vector added to its negative is always the 0 vector. Okay, and what happens here? What happens there? Well, a vector added to its negative is always the 0. Is always the 0 vector. So that's going to become the vector 0u plus the 0 vector, and adding the 0 vector to any vector is the vector. Okay, so 0 times any vector u is the 0 vector. Okay. All right, so let's look at the second problem again. If you look at the scalar multiple of the 0 vector, that's going to be the scalar multiple of the 0 vector added to itself. We know that 0 vector added to itself is always the 0 vector. And again, we use the axiom. We use the distributive axiom. I think it's axiom 8, if I'm not mistaken. We can just go and verify that. If you go and look at, if you go back there to your axioms, okay, and you look at this distributive, sorry, it's the 7th axiom, your distributivity axiom, right? So that distributivity works. Then k is going to distribute in that way. So k is going to distribute over that sum. All right, so you've got k 0 plus k times the 0 vector. And again, you apply on both sides. You add the negative of a vector, which we know exists because this is a vector space. So we can do all of these things, and there you've got on the right, what you do on the left, you must do on the right. Okay, so you must add the negative of the vector of the, okay, and so again, adding a vector to its negative is going to be always the 0 vector, and this is also going to be the 0 vector. Okay, so that then becomes the 0 vector on the left, and there we've got a vector added to its 0 vector, and we know a vector added to the 0 vector is just the vector. Okay, so that then takes care of this property here. Alright, if you look at 3, 3 is very similar. If you look at -1, the vector u. Okay, if you look at that quantity there, if you look from 1, okay, so from 1 you have that the 0 vector, you can write that as 1 plus minus 1 u. Okay, and the 0 vector, 0 times u is the 0 vector. Okay, so remember that, and then from there we have again the distributive law that holds. So you've got -1 u, and that according to 1 is the 0 vector, and the 0 vector has properties, and we know what those properties are. You add on the left hand side with the negative of a vector of the vector u. Okay, right, you add that, what you do on the left you must do on the right. You must add again the negative of the vector u there. All right, and what is a vector added to its negative? What is a vector added to its negative? It is the 0 vector. Okay, and you're adding -1 of that vector, and that is going to be -u. Because again the 0 vector added to any vector is just the vector. Okay, so you're just applying your laws. You're strictly applying your laws. So therefore that implies that -1 u is going to be -u. Okay, so the negative of a vector you can basically see as a scalar multiple of the vector, and the scalar you're using is -1 in this case. Okay, and the last one is not difficult to show, so let's assume the scalar multiple of u is the 0 vector. Right, then if k is 0, we are done. Okay, because then we have that either that one holds or that one. In case of k equals 0, we know it holds. So we're done. Okay, so assume k is a non-zero scalar. Alright, then we said that we assume that k is equal to 0. So what you can do is you can multiply on the left with 1 over k. What you do on the left you must do on the right. Okay. Okay. Alright, what do we have? That part there, we apply property 2, which says it's a scalar multiplied by the 0 vector is the 0 vector. And here on the left hand side we apply our distributive law. So the 1 over k becomes that. Okay, and then we know that k times 1 over k is 1. And we know by axiom 10 that 1u is u, and so u is the 0 vector. Right. All right, now remember what I said here. Failure of any one of those properties is a useful way of showing the space is not a vector space. Now what I mean by this is, let's look at the following example. So let V be the set of all two tuples, u1, u2, where u1 and u2 are both real numbers. And I define the following operations. I define addition normally, like I would in the normal case, and scalar multiplication I define like that. So what I do is I multiply the x component with the scalar k, and I make the y component 1. So now the question is this a vector space? So let's try and use theorem 1 to do this. Theorem 4.1.1. Okay, let's look at the first property here. If you look at this property, now that property says that the scalar multiple of u, where the scalar is 0, is the 0 vector, and let's see if it actually holds here. All right, so we're going to take that quickly and do that. All right, so we claim what we claim is we claim that V is not a vector space. All right, so how we do this, again, let's assume V is a vector space. So all the axioms hold, theorem 4.1.1 holds, is a, is a vector space. Is a vector space. Alright, so what is the 0 vector? Alright, so note that the 0 vector is the vector 0, 0. Now why is this the case? Why is that the case? Alright, we can say it's because if you take any vector u and you add that to 0, we know by our law, we know by this law here, we know that is u1 plus 0, u2 plus 0, and that is u1, u2. Alright, and that is also equal to 0, 0, plus u1, u2. Okay, so we know that. So we know that is the 0 vector for sure. Okay. So now I want to see if my theorem 4.1.1, if the first property, if that holds. Okay, so by theorem 4.1.1, we have that 0 times the vector u has to be the 0 vector. Okay, now if we look at 0 times the vector u, 0 times the vector u is now what I'm going to do is I'm going to use the scalar multiple there, or the scalar multiplication. So that is that's going to be the vector 0 with u1, u2, and according to my law, that is 0, u1, comma 1, right? And that is the vector 0, 1. Okay, so what else do we know? What else do we know? Remember that we said from there u times 0 times the vector u is the 0 vector. Now remember, that thing there is the 0 vector, so that needs to be equal to the 0 vector. Okay, so what can we say? What is the conclusion that we can derive from that? We can say that we know the 0 vector is this vector here. Okay, so that is the vector, that's the vector 0, 0. Now this is impossible. This is impossible. Why? It's impossible because the ordered pair 0, 1 and the ordered pair 0, 0, it is obvious that those two things cannot be the same because the y components are different. So, so we obtain a contradiction. So we obtain a contradiction. We obtain a contradiction. So we obtain a contradiction. So thus V is not, it's not a vector space. Okay, so theorem 4.1.1 you can use via contradiction to show a space is not a vector space, provided you know what the 0 vector looks like. Okay, so you can use the other properties in the same way to try and find a contradiction.